Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be picking up again our discussion of solutions from back in Chapter 4. Now that we've talked about intermolecular forces, we're really ready to take a deeper look at solutions. Now, solutions are homogeneous mixes of two or more pure substances. One substance is your solute, and it disperses uniformly through another substance, your solvent. And unlike what you probably used in previous years, elementary school, middle school, don't think of it as the solute gets dissolved and the solvent does the dissolving. Think of it as the solute that's present in the lesser quantity and the solvent is present in the greater quantity. Because not all types of dissolving really involve a solvent acting upon a solute. Now, solutions can be mixes in any state, and the state of the solution itself really depends upon the state of the solvent and the solute. Now, one of these states is always going to form a solution, and we'll get to why in a second. But when you mix gases, they are always going to form a homogeneous solution. Now, how does a solution form? In other words, the process of solvation. One way in which it occurs, dissolving occurs, is through the process of solvation. The solvent pulls solute particles apart and surrounds them or solvates them. Now, if our solvent is water, we call this type of solvation hydration. And this is the type of solution that's being formed where one substance is really acting upon another, involving intermolecular forces. But not all of our solutions form this way. Another method is dispersion. So when we don't have any strong solute-solvent attractions that are forming, then really what's happening is the particles aren't very much attracted to each other and they just randomly spread out. And this is pretty typical of nonpolar solutions of gases. Now, the ability of two substances to form a solution really depends upon two fundamental factors, and this is why we had to wait to come back to this concept. One is understanding the intermolecular forces involved, and two is the natural tendency of a substance to spread out into larger volumes when not restrained. And we're going to take a deeper look at both of these. Now, in the case of situation one, intermolecular forces, you need to understand there's three intermolecular forces that we're studying and looking at in the formation of a solution. One, we have to break apart the solvent particles from each other. And those solvent to solvent attractions have to be overcome if they're going to separate and dissolve something else. Well, breaking intermolecular forces is always going to take energy. So that's always an endothermic process. And depending upon the strength of the attractions, it's going to be more or less energy we have to spend. The same thing is true with our solute to solute attractions, although some of these can be significantly stronger types of attractions, like ionic bonding when it's an ionic solid that we're throwing in, something like water. But as we're bond breaking, this is also an endothermic process. And then finally, we have the exothermic part of the process, the formation of new bonds when our solvent attracts to the solute. That's actually going to lower potential energy and release energy when that bond formation occurs. So that's going to give us back energy. So we have two things where we're spending energy and one where we're forming these attractions. And remember, one ion may have many water molecules surrounding it, so we end up forming a lot of these attractions in solution. Now, when you look at force one, the solvent-solvent forces, it really depends upon what type of solvent it is. Typically, these are all molecular substances we're looking at in the dissolving process here. So they're either going to be polar or nonpolar. If they're polar, we have either hydrogen bonding or dipole-dipole. And if they're nonpolar, the force of attraction between the solvent particles would be the much weaker London dispersion forces. Now, in our solute to solute attraction, we not only have our molecular situations, our hydrogen bonding and dipole-dipole, and our nonpolar London force situation, but we also might have an ionic substance or a metallic substance that we're putting in solution. And those involve significantly stronger and more energy to break than our molecular, weaker intermolecular force attractions. Now, in the case of our solute to solvent force, this is the giving back energy. This is the exothermic part of the process. As the two particles attract each other and they move closer together and that attraction strengthens, they're going to lower potential energy and therefore more stable, and they're giving back energy. And once again, it really depends upon the strength of the attraction as to how much energy we're getting back. If it's the ion dipole, which we talked about in the intermolecular forces chapters, or hydrogen bonding, or in the case of two polar molecules coming together without hydrogen bonding, that would be dipole-dipole. And those are stronger types of attractions, so they're releasing more energy. And then we also have very weak attractions forming when we have ions next to a nonpolar substance, a polar molecule next to a nonpolar substance, or two nonpolar substances attracting each other. And in general, those are much weaker, much less exothermic situations. And that's really important in understanding our solvation process. Now, to look a little bit more deeply at this in a couple of different situations, we know NaCl, table salt, is soluble in water, and it's really because of that ion dipole attraction. Remember, that's a very strong type of attraction, so we're getting back a lot of energy at this point, and that must mean that that ion dipole attraction that's being created must be strong enough to overcome the lattice energy inside the ionic compound and dissolve it. Because we know it dissolves, we know that's happening. Now, in the case of an ionic substance with hexane, a nonpolar substance, it's insoluble. And it makes sense if you think about it. The solute to solute breaking that we talk about in energy 2 is going to be a lot of energy because we're talking about breaking ionic bonds. But when we make our bonds, we only have a much, much, much weaker ion nonpolar London attraction. So it's an induced dipole causing, because we have an ion in a nonpolar substance, that's not a lot of energy coming back. That's not going to make up the difference and allow this substance to dissolve. So really, it just takes too much energy to break, and we're not getting back enough energy to make up for it in the bond making phase, energy 3. Now, if you take a look at the energies individually, 1, 2, and 3, you can see energy 1 and energy 2 breaking the solute particle, or sorry, energy 1 breaking the solvent particles, energy 2 breaking the solute particles are always endothermic, and then forming that bond between our solute and solvent is always exothermic. But overall, what's happening in the reaction depends upon the amounts of those energies. So really it depends upon our delta H's of our 3 steps and a comparison of the two to see whether the process overall is endo or exothermic. In this case, 3 is bigger than 1 and 2, so this would be an exothermic process overall. Now, one of the natural trends in the universe is that reactions that increase, or I should say reactions that release energy, tend to be more spontaneous than those that don't. And by spontaneous, I mean it's occurring with outside intervention. It just is automatically happening. Like in the case of table salt dissolving in water, that spontaneously dissolves. So a fundamental idea here is things aren't going to occur spontaneously unless the energy of the system is lowered and you're becoming more stable. So overall exothermic would make sense why those type of dissolving reactions are indeed spontaneous. The question really is, we also have endothermic processes when overall 1 and 2 are bigger than 3, but we still know it dissolves, so we know it's spontaneously reacting. What is making up that difference in energy? So why are endothermic things dissolving? From an energy standpoint, just looking at intermolecular forces, it doesn't make sense why these would potentially be spontaneous. So there must be more at play, and that's where our second situation comes into focus here. The natural tendency of substances to spread into larger volumes when not restrained. Now, what we're really talking about here is something we're going to get to at the end of the year when we get into thermodynamics, and that's the concept of entropy. At this point, for this chapter, while we are going to talk a little bit about energy, and that's really a more correct way to understand entropy, honestly, fundamentally, think of whenever you're increasing in disorder, then your entropy is increasing. It's really about a dispersal of energy, but for this time in chemistry, I think it's easiest to think about it as the amount of disorder. So dissolving, when it occurs, is a spontaneous process. So reactions that increase in entropy, just like those that are exothermic, tend to be spontaneous. So entropy, remember, is increasing in disorder. Well, think about solutions forming. You're always breaking apart your solute and solvent and dispersing them in each other. So that's going to involve, when it occurs, an increase in entropy or disorder of the system. And if you think about that and understand what that means from an energy point of view, it makes sense why some endothermic reactions dissolve. So really what's happening in this case is when we have a situation where we're increasing in disorder, we have these two gases that are separated in a container. When we remove the separation, they spontaneously mix with each other and disperse. And because that's increasing the amount of disorder, we have an increase in entropy. Well, fundamentally, what happens is when we increase in entropy, the system is going to a lower potential energy. In other words, energy is being released when we look at the potential energy before the dispersion and after the dispersion. So therefore, diffusion is a spontaneous process, always, because we don't have really much in the way of intermolecular forces here to worry about to mean they won't mix with each other. But when we have non-gas mixtures, then we have to look a little bit more deeper and also include the enthalpy part of this. But fundamentally, it is true that when you're increasing a disorder, you're lowering the overall potential energy, and that gives us energy back. So even though the enthalpy overall may increase, an endothermic situation, the overall energy of the system can still decrease if the system is becoming more disordered. And that's always happening when we're dissolving. And this can bridge the gap. And that's why endothermic things can still spontaneously dissolve. So if we put it all together and look at what we've been talking about here, what does this really mean, these two things about solubility and dissolving? Well, if energy number 3 is greater than or close to energy 1 and 2 totaled, then the substance is going to spontaneously dissolve. It doesn't have to be more like the exothermic situation. It just has to be close, because remember, we're increasing the amount of disorder, and that increase in entropy means we're lowering the overall potential energy of the system, and that can bridge the gap, and it can still dissolve. So a simple way to look at this is number 3 comparable to 1 and 2? If they're comparable, then it's going to dissolve. It doesn't have to be more. It just has to be close enough. So is number 3 comparable to 1 and 2? That's our fundamental idea behind dissolving and solutions. So what type of solute and solvent combination tends to lead to this? Well, when your polarities are similar, 3 is typically comparable to 1 and 2. And that's where we get the term like dissolves like, which we're going to talk more about in our next set of notes. Now, before we get off of dissolving, I want to talk about one common misconception. A lot of students see a substance disappearing and think, okay, it's dissolving. Well, remember, just because two things are interacting in some way doesn't mean it's a dissolving reaction. You need to understand that dissolution, is a physical change. And you should then be able to undo that physical change by evaporating away your solvent to get back your original solution, or your original solute. If that doesn't occur, that meant it wasn't dissolving, it was chemically reacting. So be careful when you're not dissolving and you're actually chemically reacting. Chemical reactions are not what we're talking about with dissolving. Now, the next thing we're going to get into is one of our important ways to classify different types of solutions: saturated, unsaturated, and supersaturated. In a saturated solution, the solvent holds as much solute as possible at that temperature. And the dissolved solute is actually in dynamic equilibrium with the solid solute particles. If you see undissolved solid on the bottom of a solution situation, it's not actually not dissolving. It's just that the rate of recrystallization equals the rate of dissolving, and therefore it looks on the surface like nothing overall is happening. But you will definitely have a saturated solution in this. So if you ever see undissolved solute, you know right away it's saturated. If you don't see it, you don't really know if the solution can hold more, or it's full, but we just don't have extra in there. And that brings up the unsaturated solution. If we have water molecules free to continue hydration, then we haven't dissolved as much as we can in that solution at a given temperature. And that's another thing we'll get into in the next chapter, is the role temperature plays in this. And therefore, we would have an unsaturated solution. Now, the last one is the oddest situation. In a supersaturated solution, the solvent is holding more solute particles than is normally possible at that temperature. So how can that happen? You shouldn't have more dissolved than you should. Well, that's an unstable situation, and usually crystallization can be induced in these situations by either adding a seed crystal or scratching the side of the flask. Uneven surfaces can give it a site of recrystallization, and once it starts to come out of solution, the rest of it that wasn't supposed to be dissolved comes out of solution as well. Well, how can we make this situation true? Well, one, not all substances can supersaturate. But if you look at this graph on the right, you can see that in most situations with solids that are ionic in water, or molecular solids that we put in water and dissolve, As we increase the temperature, in general, the temperature tends, or the solubility tends to increase. So if we heat our solution so it can dissolve a lot more, and then we completely dissolve a larger quantity, and then we slowly cool it back off, we hit a point at which it should start to recrystallize. Some substances will automatically start to recrystallize, but some substances need a start to get that reaction going. And those substances stay dissolved and hydrated. And remember, the water molecules actually stabilize the situation by separating our ions from, or solid particles from, attracting each other. And they stay dissolved even though they're not supposed to. So some substances can form supersaturated solutions. A good example of that most of you have at least some experience with is the idea of rock candy. It's a supersaturated solution of sugar, which very slowly recrystallizes, and you can then end up growing very pure crystals of sugar. And that finishes our first set of notes on solution chemistry.